So, of course, apart from the in-house research group, we are advised and helped by the International Advisory Board, which is headed by David Ross, a programs committee, where anyone can submit proposals, as was the case this time with Emmanuel and Mahendra and Stephen, and also a strong associated faculty and visiting scientist program. So just to give an example, the schools which are happening right now and over the next 2 months, to give a flavor of what we try to do, there's the advanced string school happening this week in the building next door. Then we have summer schools on gravitational waves, statistical physics, of course, algebraic surfaces, quantitative systems biology. And just to give an example, so of course these programs are not only organized by people from the institute who are members of the institute, but also from across the world. So for example, the STATFIR school is run by Joel Lebowitz, quantitative biology by Antonio Celani, some of us in this room know quite well. And also this month, the public lectures that are there at ICTS, and I strongly encourage, in case any of you are here and are bored of dynamos after the second or third day, so there will be lectures by a whole bunch of people, like Britain, Boris Schreiner on systems biology, Britain, Papa Strominger on string theory, Manjul Bhargav, who won this year's Fields Medal on the relation of mathematics and poetry, and these are things which go on throughout the year. Alright, so that's the last slide. So this is what the campus will look like. It's about 10 kilometers from here. We were hoping that we'll kickstart the campus with this program, but I got nervous at the last minute and decided to stick to doing it here. But hopefully the next time we see you, it will be there. And with the guest houses there. Okay, so with these words and the slight introduction to where you are and why we are here, I'd like to ask Emmanuel, who's the chair of the GdR, to formally set the ball rolling. Thanks.
I don't have much to say, but thank you for being here. So you're all part of this program that's running for years, and it's been very recently extended to international. Actually, this is the first time that the GdR meeting is outside of Europe, and so I'm very pleased it's here in India. And I'd like to thank our guests for organizing it. Because I'm really, you already did the presentation. I think we want to thank Mahendra Verma, and that you can stand up, who also took part in the organization. And Manasi, the secretary of ICTS, which is not here now, we have to thank her for the end. Okay, and so Stefan also took part in the organization, but unfortunately could not be here for the conference. Maybe we should give a few details on the week. So there will be a conference dinner on Tuesday evening.
Yeah.
That.
Yeah.
So keep your Tuesday evening free. If you have friends in Bangalore or birthdays, better to see them. And also there is a Wi-Fi room. I'm not sure if you are given the password or not. No, maybe.
Yeah. Okay. I should take care of that. Thanks.
So this is pretty much it. And enjoy it.
Just to add to what Emmanuel said on the logistics and so there's our just to add to the So just to add to what Emmanuel said, breakfast is served in the balcony. The tea coffee breaks will also be in the balcony where some of you have been. The lunch will be at the balcony, and tomorrow is the conference dinner. I will sort of provide details a bit later because we are still trying to gauge if it will rain tomorrow evening, and depending on that, either we'll have it on one of the lawns on campus or shift to a restaurant downtown. Okay, so Arnav, you wanted to say something about something? And the Wi-Fi password is here.
Though I am not an official organizer, I was requested to say a few words here, presumably for two reasons. Firstly, I am a professor at IISc, and this meeting is being held. So on behalf of IISc, I wish to welcome you all and hope that you will have a pleasant and scientifically fruitful stay here. And the second reason why I was asked to say a few words is a little odd, that I happen to be the first person to work on dynamo theory in India. So the organizer felt that by looking at me, you may have a kind of a sensation similar to the sensation you get by looking at a dinosaur skeleton in a museum or something. Anyway, so when I first started working on dynamo theory, on solar dynamo problem nearly a quarter century ago, at that time not only nobody else had done any research on dynamo theory in India before that, even within the Indian academic community, realization of what dynamo theory is was very limited. So when I would tell people that I am working on the solar dynamo problem, most people would assume that I am to build a dynamo powered by solar energy, and then people would even congratulate me by doing something which may benefit human society someday. So I would tell them, I would tell that I have disappointed you that and I am doing it because of my intellectual curiosity, and there is not much chance that my research will be useful in the near future. So anyway, so I think my first paper, which came out in Astronomy and Astrophysics in 1992, that was presumably the first paper of dynamo theory from India. So in which we argued that we discussed what are the causes of irregularities of the solar cycle. Even at that time, I used to think that so dynamo theory would die in India with my retirement. But then I was happy that over the years, many of my colleagues who began in other fields eventually got gravitated to dynamo theory. For example, last year we had Bangalore with us, so who began with his PhD thesis on things like quasars and gravitational lensing. So I played a little bit of role in bringing him to dynamo theory. I think I used to tell him that how exciting dynamo theory is and he should take interest in that. And then in my own department, I have my colleague Rahul Pandit, who began as a condensed matter physicist, but then first shifted to fluid turbulence, then to energy turbulence, and then is taking interest in the dynamo problem. And Mahendra Verma in IIT Kanpur was also started with MHD turbulence and then moved to dynamo theory. And now some of my former students are also building up solar dynamo groups in different places in India. For example, my former student Dibbendu Nandi has initiated a thriving solar dynamo group in Kolkata, and then we have Vinod Srinivasan, who after his initial training with stalwarts like Chris Jones, first shifted to Kanpur IIT and then shifted here. So even though the dynamo community in India is small, it is, I would say that it is a sort of a thriving community, and I hope that these kinds of meetings will help us grow further. So unfortunately, in this week's meeting, we do not have as much representation from Indian dynamo community, especially solar dynamo community, as we wish, because exactly this week there is also a conference on solar dynamo in Boulder, and some of my former and present students are attending that conference. But anyway, still our friends from abroad will have some idea of Indian dynamo community, and I hope that these kinds of meetings will help us have more interaction within the dynamo communities inside India and outside. So, well, I think enjoy the meeting and warm welcome to all of you again. And so, anything else to say, or we should?
No, I think that's fine.
Okay.
Start. Okay.
Okay.
Right.
First session will be chaired by Professor Rajogli.
Right.
So the first keynote talk is by Professor Chris Jones, who needs no introduction. So he is from Leeds University. So he will tell us about torsional waves in the arts code.
Thank you very much. Thank you very much indeed, and thank you for the invitation. I have to say it's my first visit to India, and I'm enjoying it very much, particularly the hospitality which we've all experienced here. So let's get this going. Okay, so that seems fine. So I'm going to talk a slight change in title. I'm not just going to talk about torsional waves in the Earth's core. I'm going to talk about a bit of other work, more recent work on waves in the Earth's core, a different kind of wave, the magnetic Rossby wave. But first of all, let's make sure we understand who's done all the work behind this. So the torsional oscillation part has mostly been done by Robert Teed, who was at Leeds and is now in Cambridge. And the magnetic Rossby wave stuff has been done by Kumiko Hori, who is visiting Leeds on a Japanese fellowship. So let's get going. Maybe this works. Is this? Yeah, okay. So first of all, let's just discuss what we're talking about here. So this is the interior of the Earth, and in the liquid metal outer core, the dynamo is taking place, and it's driven by convection arising from heat and light material, most of which is being released at the inner core boundary there. So ICB for inner core boundary, CMB for the core mantle boundary around here. And that convection, of course, stirs up the fluid here, and the geomagnetic field is generated in this liquid metal core. We measure it at the Earth's surface out here, and we convert it into spherical harmonics, and using the fact that this part of the mantle is basically insulating, not totally, but basically insulating, it is essentially a potential magnetic field, so we can extrapolate it down to the core mantle boundary. And if we do this, we get the following pictures. So this picture here is what you see at the surface, so that's the radial magnetic field actually at the surface, and you can see the slight weakness here in the field, the South Atlantic anomaly. And this is what you get if you extrapolate that field down to the core mantle boundary. Of course, the small scale features are much more brought out by this. And we see flux patches all around, two big flux patches, one over Canada, one over Siberia. This string of wave pattern, or apparently a wave pattern there, which is slowly drifting westward, and some reverse flux here, which is the weakening, which leads to the weakening of the magnetic field in the South Atlantic, the famous South Atlantic anomaly. And these flux patches move in time, they drift. Sometimes they come up and sometimes they come down. Over in the Pacific, the drift is somewhat eastward. In the Atlantic hemisphere, the drift is somewhat westward. But the time derivative of the spherical harmonics is called the secular variation, and that is fairly well mapped out for the last 300 years or so. So why do we want to study waves in the core? Well, the magnetic field in the Earth varies from many time scales, from time scales down to, this is about the smallest time scale that we can actually see in the range 1 to 300 years. Of course, on much longer time scales, there are reversals occurring on a time scale of about 250,000 years. And on even longer time scales, you have things like the Cretaceous superchron, where the magnetic field has been the same sign for 60 million years. But for these waves here, we actually have the data. So by identifying waves in this signal, we can potentially discover what the strength of the magnetic field actually in the core itself is. We can only observe BR at the core mantle boundary. We're essentially ignorant of what the azimuthal field is. The dynamo model suggests it's going to be somewhat stronger than the radial field. And the dynamo models also suggest that the radial field itself is likely to be substantially bigger inside the core, than it is at the surface where we actually observe it. So we're expecting to discover stronger fields from by studying these waves. Now, waves on these timescales are, of course, MHD waves affected by rotation, magnetic field, and the spherical geometry. But a lot of types of waves are possible. Fast waves are possible on the rotation, the inertial waves on the rotational timescale. Very slow waves are also possible. But we're going to be focusing on the waves which are in this range here, because these are the periods in the observable range. So although there are lots of modes, it's these ones which have this kind of period which are of particular interest, and those are the ones that we have the data for and are going to tell us something about what's going on in the core. And there are basically two types of waves that are known which fall into this category. There are the axisymmetric torsional oscillations, which have periods about 6 years, and that's about the travel time of Alfvén waves. There's strong evidence, I would say, that these waves have been detected in the core, and the key question is how they're excited and what determines their period. And I'm going to be talking today mostly about these questions here. So the other kind of wave that I'm going to be talking about are the magnetic Rossby waves. These are non-axisymmetric. They typically have slower periods, typically a few hundred years, but there's a whole range, of course, depending on the wave numbers involved. The secular variation itself has non-axisymmetric and axisymmetric components. So for the torsional oscillations, we separate out the axisymmetric components, and for the magnetic Rossby waves, we're looking particularly at the non-axisymmetric components. Now, the situation about magnetic Rossby waves is quite a long way behind the situation for torsional oscillations, because torsional oscillations, we have strong evidence that we can actually see these in the core. I can't really honestly say that we've unambiguously seen magnetic Rossby waves in the core, and the reason for the difficulty is that it's very difficult to tell what is a magnetic Rossby wave with a phase speed of a few hundred years, and what is a much slower wave that's moving because it's advected by the mean flow. So we have this thing called the westward drift, or there's a general view that the core is moving slowly, and sometimes people have thought that maybe these waves, these patches that are drifting across, are just essentially stationary waves which are being advected by the fluid speed. And of course that's less interesting in a sense, because it's not the dynamics of the wave then, it's just telling you what the drift speed is. It doesn't actually tell you anything about what the strength of the magnetic field. If you can actually see the wave part, the dynamical wave part of the signal, then that of course would tell you what the magnetic field strength actually is. So the difficulty has been separating wave motion from advection, and as I said, it's been controversial whether it's due to wave or core flow. I think probably most people believe it's mostly due to core flow, but I think it's likely a combination of both. And really the task is to separate out that which is due to core flow and that which is due to wave motion. And Kumiko Hori's recent work is all about trying to look at what sort of waves, whereabouts in the secular variation we should be looking to give us the best chance of actually separating out the core flow advection from the actual wave dynamics.
Chris, what's the difference between a magnetic Rossby wave and what we're basically calling MC?
Well, I'll tell you exactly about that when I get on to that.
Sorry.
You're jumping the gun there, you see. They are a particular type of MC wave. They're a particular class of MC waves, certainly. Okay, right. So stably stratified core. Now, a potential complication of the whole story is that it's possible that the top few hundred kilometers of the Earth's core is stably stratified. Again, we don't really know whether that's true. Some people have strong views that it is, some people have strong views that it isn't, but there isn't really too much evidence out there yet that there is a stably stratified region. There are several reasons why we might expect it. We don't know what the total heat flux going from the core into the mantle is, but it's quite likely not massive. And certainly with the more recent values of the thermal conductivity, it is entirely possible that all the heat flux is being carried by conduction, actually right just underneath the core mantle boundary, in which, of course, there won't be any need for any convection there, and so then the core won't be convecting up there. So it could be a stably stratified region at the top few hundred kilometers. Another possibility is that all that light material, which is released when solid iron or purer iron goes onto the inner core, that leaves light material which sort of floats up. Maybe that just mixes into the outer core. Maybe it floats all the way to the top and forms what Brzezinski called an inverted ocean, i.e. a stably stratified layer under the CMB. Now, if that layer exists, it'll certainly modify the waves there, and it gives rise to new internal gravity waves, so there's a whole new class of waves, and they may well be important, but there hasn't been much exploration of these waves yet. And in fact, actually, identifying these internal gravity waves, I think, is the most likely way that we'll actually be able to confidently assert that there is or isn't a stably stratified zone at the top of the core mantle boundary. The timescale of the waves, well, it depends on the amount of stably stratified layer. Basically, it modifies the MC waves into Mach waves. So basically, it will generally speed them up somewhat. I'll say a little bit when I get to the actual dispersion relation later on. This is what a torsional oscillation is, a nice picture from Roberts and Arnaud's paper. So the torsional oscillations are entirely geostrophic. That is to say, the motion is on cylinders, like so, independent of Z, so the pressure force is balancing Coriolis, and the magnetic field goes through, so we're looking at the S component of magnetic field in cylindrical polar coordinates. And as this oscillation goes backwards or forwards, it stretches out the magnetic field, and the Lorentz force provides a restoring force, and the rotation frequency doesn't appear at all in this because rotation is totally taken out because, as I say, the rotation forces, the Coriolis forces, are balanced exactly against pressure forces for these axisymmetric torsional oscillations. And to get these things, you have to have completely geostrophic motion, so vortex length must be constant, so there's no change, no vortex stretching in torsional Alfvén waves. And so we can hope to measure the magnetic field component BS by looking at the speed of these torsional waves. Okay, so here's the data. This is a picture from Gillet et al., the Grenoble group, Dominique Jolt and Gillet, and this appeared in 2010. And I'll just explain what this picture is. So this is the axisymmetric part of U phi, which is the part which will take place in the torsional oscillation. That's constructed from observations of the geomagnetic field. And this is the tangent cylinder. That's the position in the S value. This is S going out here. So that's the center of the Earth down here. That's the S value of the tangent cylinder. That's the imaginary cylinder that just encloses the inner core. And that is the outer part, so that's the CMB at the equator. And you can see that this signal is quite remarkable. You can see it's propagating waves outwards in that direction at a certain speed. And by looking at that wave speed, Gillet et al. Were able to deduce that the magnetic field, BS, is about 2 milliteslas, that's 20 Gauss in old units, which is considerably bigger than the field actually observed at the surface. But that's sort of consistent with dynamo models, which generally predict a bigger field. So that's one way we can discover, guess that these torsional oscillations are taking place. I'll just point out to you that the tangent cylinder seems to be a particularly interesting place here because the waves appear to be going in the opposite direction, i.e. towards the center of the Earth here, and they're going outward out here. So it looks as though they're being sourced actually close to the tangent cylinder. And the tangent cylinder, as we shall see, plays a very special role in the theory. The other way you can see it is length of day variations. So this is a plot of the length of day variations in milliseconds. So it's tiny, of course. I mean, this is 10 to the minus 4 of a second, this variation we're talking about. Of course, you can measure the rotation rate of the Earth very accurately. Well, I mean, this is easy to understand because as this fluid in the core is going backwards and forwards, it's changing its angular momentum. Total angular momentum must be conserved, so that angular momentum must be coming out at the mantle, so the mantle must be rocking backwards and forwards as the outer core fluid undergoes these torsional oscillations. So by simple angular momentum conservation, we understand that there's going to be a signal with the same kind of period as the torsional wave period. And interestingly, this period looks to be about 6 years here, which is about the same sort of period as these things are going off at. And in fact, recent work suggests it may be even 5.9 years, really quite accurately going backwards and forwards, but not everybody's agreed with that. Some people think that this is a bit more random. There's quite a lot of data reduction that goes on before you get to these nice tidy pictures. So there's quite a bit of wiggle room in actually interpreting the observations.
Also, the vertical dashed lines, Chris, are those the jerks?
Yes, those vertical dashed lines are jerks, like that one. There's a famous 1970 jerk, isn't there? Yeah. So, I mean, you typically see sort of slight changes in the length of day actually at a jerk time. Right, here's the dynamo model equation. So these are what we've been doing now is basically simulating trying to simulate these waves using a standard dynamo code. There's not much that's very unusual about this. This is pretty much the same sort of code as being used for the last 20 years now, I guess. Are there any special features? Well, not really. Oh, I might mention that this is fixed flux boundary conditions, no slip boundary conditions, zero compositional flux at the CMB and a uniform sink in the interior. So we're thinking of this as being driven by compositional convection, which again is fairly standard now in dynamo models. The parameters used, of course, are about much larger Ekman numbers than reality, as everybody knows. I'm sure the real Ekman number in the Earth is something like 10 to the minus 15. That's what you can achieve numerically. Radius ratios, of course. One of the reasons why we choose these is that they give sort of Earth-like dynamo models, basically dipolar, but with an appropriate amount of reversed flux patches. So the pictures look quite similar to the Earth, even though the parameters are fairly way off, because that's much too large. That's much too large too. But nevertheless, they do give reasonable pictures, and that's why we use these model equations. So that is the axisymmetric part of U phi on a meridional section. So that's the South Pole, North Pole, and I think this one is a movie. Yeah, very good. So you can see how it evolves with time. You can see it stays pretty geostrophic in the model and it moves around. So it's clearly moving, but it's not immediately clear from that whether we're really seeing torsional oscillations or not, well, any systematic oscillations. But notice the solid inner core of the Earth doesn't take part because we've got insulating boundary conditions. And notice also, of course, that because it's fairly geostrophic, the top, the southern hemisphere here is rather different from the northern hemisphere because the columns don't go all the way through there.
So the data showed a polar drift in the higher latitudes and an equatorward drift in the lower latitudes. Does the theory explain that? Yes. In fact, I'm just about to get onto that, actually. In fact, I think it almost might be it'll be, well, a couple of slides to go, yes. Alfvén wave equation in spherical geometry is that, so that's easily written down. And UA squared, the Alfvén speed squared, we take the, is given by this well-known formula. But if we have to average BS squared over the cylinder, so if you look at the cylinder of radius S, you get the Alfvén speed at the position S by doing integration over phi and over z. And then that is the wave speed. So in our numerical simulation, we have BS, so we can evaluate UA squared. And we run the dynamo simulation. The technique is that initial transients first
die away. We go on for a further time tour, which is about sort of typically 4 or 5, or maybe even 10 sometimes, but typically 4 or 5 times 6-year periods, so that we get a decent stretch here. We evaluate UA from BS and the field average over time. So, and then we make plots in the USTS plane of the fluctuating part of U phi. Now that's important. We want to look at the time varying U phi prime, because that's the thing which is taking part in the oscillation. So we subtract off the mean value of U phi over the whole Tor integration in order to concentrate on the fluctuating part. Okay, and then...
Another quick one.
Yep.
Does the fact that H has a discontinuous derivative on the counter, so that you problem?
Well, no, but it means that the picture has a discontinuity. When you actually do the plot, it has a sort of discontinuity at that point, as you will see. So, indeed, here. So this one you see is the northern hemisphere, yeah, and you can sort of see there's a line there, which is exactly that discontinuity there, and there's a line here, which is exactly that discontinuity that you're talking about. So this one here is the whole picture with the tangent cylinder north, and this is the whole picture with the tangent cylinder south. So these bits are more or less exactly the same, of course, whereas down here it's different because of and there's this discontinuity here which occurs at that line. Now the white curves here are the speed of the Alfvén wave. So if we're seeing torsional oscillations, we're looking for structures which are moving with the right speed, and you can see that there definitely are such structures in this picture. Mostly they're moving this way, actually, in this picture here. In other simulations, you sometimes see stuff moving backwards, but that's comparatively unusual. Most of it moves outward, as though it's coming from the inner core and propagating out to the boundary. There's not much evidence of any reflection. In principle, one could have reflection at the core mantle boundary, but it appears that the waves are somewhat too damped to do that. Now, so what are the good things we found? Well, we're seeing torsional oscillations in dynamo simulations. That's good because it helps us to study them. They mostly travel outwards. If the field is scaled to the observed B at the CMB, then the travel time from the tangent cylinder is about 3 years, which is similar to the Gillet et al. Data, so that's good. Minus points, well, the origin, actually most of these things seem to come from inside the tangent cylinder rather than at the tangent cylinder. The waves are not as periodic as suggested by the Gillet et al. Data. I mean, there are things going up here, but there's nothing like that nice sort of picture that was in the Gillet et al. Data. There's a very recent paper where they've redone it, and in the recent paper they point out that the speed, this is slightly confusing because for the new paper they've got the inner core boundary here and the CMB down here, so they're all going the other way, and the colour scheme's different as well. But that's going fast, and that's going slow down there. So we're getting slower speeds near the equator. And if we just go back a minute to our simulations, you can see that the same thing happens here, because it's going quite fast, and it definitely slows down as it moves out, and that's because the field is getting weaker, which relates to the question you just asked. The field is actually getting weaker out towards the more outside regions, and it's somewhat stronger actually inside. So they now give in the May 2015 paper, they now have BS 2 milliteslas in the middle, but nearer the outside, this corresponds to a slower speed of about 0.6 milliteslas. Okay, so how are these what's the excitation mechanism of torsional oscillations? How are these things actually being driven? Well, if you take the phi and the z averages, so that bar is phi average, that angle brackets is the z average of the equation of motion, so that is then the geostrophic part of the azimuthal flow. You get the equation for the geostrophic. The time derivative of that is equal to these terms, and that's the Reynolds stress, so that's the forcing there, or Reynolds force, that's more properly when we take the component of it. This is the Lorentz force, and this is the viscous force. So all these things contribute, So we can write these as FR, FL, and FV. We're only really interested in the fluctuating part because it's the oscillating part of these terms which is going to drive the oscillation. So we look at the fluctuating part and we split the Lorentz term into the bit which is the restoring force for the torsional oscillation. So that's the bit that was in the Brzezinski formula. And then there's all the rest of it, which comprises the ageostrophic parts of the Lorentz force. And I've got an R for restoring and a D for driving there. And that's the Reynolds stress part, and that's the viscous stress part. Now, in the core, the inertia is small, and so Reynolds stresses are going to be small. So we expect these terms to be much bigger than that. And this is a problem because in our dynamo models, this is not that small. Typically, this is sort of comparable to this. But it's very unlikely to be that in the core. It's just that that's where you can get to in the parameter space. So what did we do? We looked at some magnetoconvection simulations. So FR prime is overestimated. Kinetic and geomagnetic energy are typically similar in the simulations. Andy Jackson presented some enormously expensive, computationally expensive simulations where the magnetic energy was bigger than the kinetic energy. But for this kind of study, I mean, we can't wait 3 years to get the answer out. We need something that's a bit more practical. And so what we did here is we used magnetoconvection. So we're not trying to solve the dynamo problem. We change the magnetic boundary condition. We impose a dipole field at the CMB. It's the same code. But that change means, of course, you don't have to wait the huge amount of time for the dynamo to actually get in and saturate and come to its basic state. The whole thing runs much more quickly. So that's good. So it's a bit of a cheat in a way because it's no longer a full dynamo problem. But since we're only interested in periods of a few hundred years when the field hasn't changed all that much, it's actually quite a sensible thing to do. And it enables us to get to parts of the parameter space you wouldn't otherwise be able to get to. OK, so here are some results. What we've plotted here is what's called the geostrophy ratio, or at least we call it the geostrophy ratio. So that's the geostrophic part of the fluctuating signal, dash for fluctuating. All these bars and things means it's the average integral over the cylinders at radius s, and we divide that by the total fluctuating part, and at various parts of the parameter space, we get different amounts of geostrophy. So the bigger the geostrophy ratio, the bigger the torsional oscillation component of the whole signal actually is going to be. So with the dynamo stuff, we were only down here, just about able to see torsional oscillations, but not terribly clear. Now we can get sort of up here, and indeed we can get right up here, which is actually where the torsional oscillations are the dominant part of the signal, and so it's much easier to see what's actually going on. And we can also get to much lower Ekman numbers. That's actually the magnetic Ekman number. That's the eta over omega d squared there. So in the Earth's core, this is about 0.45, so it's sort of in the middle of these pictures. And as I say, that's a good place to be. Basically, so then the oscillation would then be basically a Mount-Buffett type oscillation, and my stuff on the tangent cylinder, these waves on the tangent cylinder provide broadband forcing, and that broadband forcing then selects out that particular, resonantly picks out that thing, and that sends the waves, that sends the torsional waves off. So I mean that's quite a nice, that's good because it sort of goes quite nicely with the data actually. In
your simulations, you mentioned at some point that
the simulation.
You have a periodic release of the waves.
Well, they are fairly periodic, yes.
It's periodic, but you have no oscillation on the
no oscillation in the core. That's right. So in a sense, I mean, we could say that we don't need this convection in the inner core. That's possible, and I mean, I think Rob is quite keen on that theory. But my only caveat would be is that, yes, they are fairly periodic, but because they're going to depend on which wave number is forced, I mean, that was sort of m equals 20 being forced there. I mean, it's sort of hard to believe that it really stays on m equals 20 for long periods of time, I would expect to see a bit more wave drift. I wouldn't expect to see a 5.9-year regular oscillation. And I mean, if the magnetic, since these things also depend on the magnetic field, as the magnetic field varies over time, as we know it must, then that again would change the period. So I think that, I mean, you can get periodic solutions, you can get periodic waves like that. They're, I think, almost certainly not going to be fantastically stable in period. So I think we need to go back to the data again to see how reliable that 5.9. Now, Richard Home is a great believer that it is actually a stable 5.9-year oscillation. The Grenoble group are somewhat less clear about that. They think there could be some variability. Now, if there's some variability, then maybe we don't need the Mound-Buffett oscillation at all, because then if there's some variability, then these waves, which are basically waves, they're traveling around the inner core boundary, that might be enough.
But sometimes they don't see them.
So,
Sometimes they don't see them.
yes.
The observations.
Yes, sometimes you don't, that's right. So, I mean, yeah. So, yeah, so, I mean, yeah, so I think it's still a bit out. I mean, I think there's always going to be two schools of thought here, and we'll just have to wait for the data to make to decide on this. But I mean, as I said, there is new data coming in all the time, so I mean, it's not hopeless. I mean, we are going to be getting more information and better information as time progresses. Yeah.
The second part of the lecture, waves in the earth scope.
Yes.
V naught, the basic magnetic field V naught is constant.
In the theory, yes, that's right. Yes, that's right.
Variable.
Well, yes, when we do the dynamo models, yes, of course, B naught is not then constant. B naught then varies. So you see, we see then a local wave speed, yes, depending on what the value of B actually is. So in the dynamo models, B phi varies as a function of S, the distance out, yeah. And since we're essentially geostrophic, we're integrating over these cylinders again to get the B phi, but it's a function of S. And that's why you get a different wave speed, yeah, depending on where you are in radius.
In that case, will there be singularities in the equation?
There are places where there are places where B phi goes to 0, yes, where the wave speed would go down to 0. Yes, that's true. Yes, in practice, these won't actually occur in the real life, because there will always be BS components of magnetic. If you've got a B phi component of 0, it's very unlikely the whole field will be 0, and there will be BS, non-zero BS components. So there will still be a finite wave speed, because you'll still get oscillations due to the bending of field lines in some direction. Yeah.
Another question?
Actually, you mentioned that it's the geostrophic part of the flow that matters. And of course, when
yes.
you have here the tangent cylinder, what comes from above and below the inner core is different.
Yes.
So this is
Yes.
a good reason for...
No, yeah, yeah, it has to be geostrophic there. That is absolutely right. Yes, yes. Yeah, I mean, the purely geostrophic part of U phi prime is the bit that goes into the restoring force, and that's the bit that goes into the Brzezinski torsional oscillation, yeah. But the forcing, of course, has to be an additional term, different from that, and that's why this forcing is the ageostrophic part.
Any other question? So I have a question about this torsional waves part.
Yes,
so
yeah.
you pointed out the data shows more regularity compared to results of your simulation. So what do you think this signifies, that the actual magnetic structure is...
Well, I mean, in the sense that the frequency is more regular, this, I mean, this, if that's really true, yeah, then that would support the Mound-Buffett theory, that the thing that's missing in this simulation is the gravitational coupling of the inner core to the mantle through this non-axisymmetric gravitational potential, because the geoid is slightly egg-shaped, yes, and that can give rise to this oscillation of the inner core relative to the mantle, which of course could be, because it's gravitationally controlled and therefore doesn't change over time, it could be more regular. So, yeah.
Okay, thank you.